worksheet. Stapled one. Yes, it is. Do you need one of these, Quinn?
Yes, thank you so much.
You're welcome. We left off last week with the distinction between inter and intramolecular reactions. How could you briefly describe the difference between those? Good. Anything else you guys want to add to that? One happens within a molecule, one happens between different molecules. We noticed a trend about intramolecular reactions, right? Intramolecular reactions form rings because one part of a molecule is reacting with another part of the same molecule, and that's going to create a new point of connection between that same molecule. Having these nice clear lines in the sand isn't always easy to decide what is inter, what is intra. For instance, the intramolecular reaction on the bottom right shows elemental bromine, which is a different molecule, and part of that bromine ends up on the product, which means, is it really intramolecular or is it also intermolecular? The alkene interacts with the bromine, intermolecular, but then the alcohol reacts with the intermediate that forms, intramolecular. So I rarely will ever ask you guys to decide, is this inter or intramolecular, because it is a little weird. Sometimes it feels like it's both. Also with those intramolecular reactions, it gets a little bit harder to say, are we doing substitution, addition, or elimination? For instance, when we learned about addition reactions, we said that addition reactions consume a pi bond, and usually that means decreasing your degrees of unsaturation. But this reaction on the bottom right goes from 1 degree of unsaturation, the pi bond, to 1 degree of unsaturation, the ring, which is a little bit more characteristic of substitution, where you conserve the degrees of unsaturation. But there is a pi bond consumed. So the reaction that's intramolecular, but also kind of intermolecular, feels a little bit like substitution, but also looks a little bit like addition. So we are trying to come up with categories, but nature doesn't care what categories we try to invent. There's always going to be some blurred edges between these boxes. All right, so let's flip it over to the next side. We're going to talk about section 3. No, unit 2, regiochemistry and stereochemistry, where things go and how they go there. So this first example, a Markovnikov type addition, named after a dead man, Markovnikov. Figuring out whether it's regiochemistry or stereochemistry. What do you think Markovnikov as a term describes? Is Markovnikov describing something about the regiochemistry of an addition reaction or something about the stereochemistry of an addition reaction? What gives you that indication, Quinn?
Well, because we don't have any, we can't see if anything is like cis or trans to each other.
In fact, there's no chiral carbons even. So what does Markovnikov's rule tell us about regiochemistry? What is the regiochemical trend that Markovnikov identified. You might not be able to figure it out until you look at the anti-Markovnikov addition example. Can you identify the regiochemistry difference between the Markovnikov addition and the anti-Markovnikov addition? With a regiochemical perspective, what is the difference between Markovnikov and anti-Markovnikov?
The position of the hydrogen.
Good. Can you describe the position of the hydrogen between Markovnikov and anti-Markovnikov? Chloe. Perfect. That's what Markovnikov identified. He found that in the reactions he was studying, H adds to the carbon with more H. Okay, are you all right with the symbols I've used in there? Another way of saying that, using regiochemistry terms that we've used, is the H adds to the less substituted carbon. And Markovnikov really truly believed that this was the best way to identify this trend. I don't think he was analyzing all of the reactions that we're going to go through. Later, people found reactions where the hydrogen added to the more substituted carbon. So they identified that as just being opposite to Markovnikov's trend, an anti-Markovnikov addition. I would like to tell you, Markovnikov's trend sucks. It's terrible. It's meaningless, in fact. Because what Markovnikov's trend gets you to think, and I've seen students think this, is that it has something to do with the hydrogens. Hydrogen goes to where there are more hydrogens, probably because they're all hydrogens. That's what it implies. H goes to the carbon with more H. Sure, maybe it likes its neighbors. It has nothing to do with hydrogen. In fact, it has a lot more to do with the mechanism of the reaction. The charge tries to stabilize itself as much as possible. And in reactions where the hydrogen goes to the less substituted carbon, the charge is being stabilized on the more substituted carbon. In reactions where the hydrogen goes to the more substituted carbon, the charge is being stabilized by the less substituted carbon. It's always about charge stabilization, and that is what directs the hydrogen to where it goes. And we're going to talk a lot about charge stabilization. But that's the trend that everybody teaches, and it's the trend I have to teach you. I wouldn't have identified a regiochemistry trend here and named it after a man. I would have told you charge stabilizes itself as best as it can. And that predicts whether the H goes more substituted or less substituted. Depends on the reagents, depends on their charge. That predicts our regiochemistry. All right, look at Zaitsev and anti-Zaitsev, or Hoffman. First of all, these are describing what type of reaction? What class? These are elimination reactions. I'm removing two groups. I'm forming a pi bond. Elimination. Not to be confused with adding alkenes to the structure. It's not an addition reaction, despite the fact that a new functional group is being formed. That new functional group is being formed because groups are being eliminated. Regiochemistry or stereochemistry? One more time for me. Yeah? It's just describing where that pi bond is going to form. And what's the difference? Does the pi bond form at the more substituted carbon adjacent to that bromine, or does the alkene form at the less substituted carbon adjacent to that bromine? It's a regiochemical difference. More substituted carbon, less substituted carbon. Zaitsev elimination says the most stable alkene forms. I love that rule. That makes way more sense. Except that I haven't taught you stability of alkenes yet. So that's something that we're going to have to explore. But what we can infer then is that the most substituted alkene forms. Except I haven't taught you about substitution of alkenes. I don't think it's hard to cover that. It follows very closely to substitution of carbons. How many carbons is the alkene bonded to? The more carbons the alkene is bonded to, the more substituted. The more carbons an alkene is bonded to, the more stable. Anti-Markovnikov then is the least stable alkene forms, which is to say the least substituted alkene forms. Markovnikov had gotten his PhD in Europe, maybe Germany, a little bit before Zaitsev was defending his PhD. And Markovnikov actually, this is some like tea, 18th century tea. Markovnikov said Zaitsev's rule, the pattern that Zaitsev has identified in his dissertation makes no sense. It's ridiculous. He does not deserve to get a PhD over what he's defending. Meanwhile, Markovnikov's rule literally makes no sense. At least somebody else had identified the opposite of what Zaitsev had identified. Hoffman identified that you can form the least substituted alkene if you use the right reagents. Markovnikov's trend made no sense whatsoever anyways. He focused all about the hydrogens, and it had nothing to do with the hydrogens. Another downfall in Zaitsev's trend is that it only applies to addition reactions that add one hydrogen. And we've actually seen addition reactions that don't add hydrogens at all. And we've seen addition reactions that add multiple hydrogens. But in those reactions that don't add any hydrogen, there is still regiochemistry. But we don't have anyone's name to use as a rule for it because Markovnikov pinned himself in a box and said, my rule only applies if there's a change in one hydrogen. So I'm going to try and teach you what Markovnikov's rule should have helped us identify, despite the fact that his rule is far too limited. All right, syn, anti, and antiplanar are all what type of descriptor? Regiochemical or stereochemical descriptors? Stereo. Syn applies to addition reactions. A syn addition means that two groups add on the same face. So we're going to learn a reaction this semester that gives us a syn vicinal diol.
Syn is always cis.
Syn is cis. And you can hear the similarity between them, right? Syn addition meaning the two groups will become cis to each other. And its counterpart, anti-addition, means that two groups add trans to one another. But I have something I need you to understand about this. in the ring, it's very obvious to see that syn addition leads to a cis diol. It's very obvious that anti-addition leads to a trans dihalide. But syn and anti are not cis and trans. Remember, cis and trans can only be applied to those rings, and really it can only be applied to di-substituted rings. If I have more than two groups, I can't use cis or trans anymore because I don't know what two I'm comparing. It only compares two groups. And they can only be used in rings because in our linear structures, we have freedom of rotation, which means things are never truly cis or trans to each other. They can look cis in one conformation, they can look trans in the other conformation. Syn and anti are not cis and trans because syn and anti describe how the reaction proceeds, not how the structure looks. Syn and anti describe how the reaction proceeds, not how the structure looks. And I want to give you an example now that takes us away from a ring. Because we know that the rings can't twist. So yes, syn addition does look like a cis diol. But if I do this on a linear alkene, a linear chain, and I form a cis diol, syn diol addition, what do we know about the structure on the right? There's a lot we know. Feel free to contribute what you know. We know it's meso. It's got a plane of symmetry right down the middle. What else do we know? We know that it went through syn addition.
It's not a ring, so it's not cis.
We know it's not a ring, so we can't say it's a cis diol. Good. Mm-hmm. We can always do a Newman projection. So would that tell you something? Would it show it to you in a different conformation? It would give it to you as a different perspective, but a different perspective of this conformation. All right, so I'm going to look down the structure this way, which means I'll have my two OHs up, my two CH3s down, and my two H's to the left. It's got, did you say torsional hydrogens?
Torsional
Tension, torsional strain.
strain.
Yes. This has torsional strain, which only shows up in what type of conformation? Eclipsed. And eclipsed conformations are always the highest energy set of conformations. They're always higher energy than staggered. And if I rotate this in either direction, I actually go from two sets of eclipsed groups. OHs are eclipsed, methyls are eclipsed. And if I rotate it into a different eclipsed conformation, I get only one set of eclipsed groups, which means that this is the highest energy conformation of this molecule. So how often would you be able to reach into a sample of this compound and pull out a molecule that is in that conformation? Not often. A very, very small fraction of this sample is ever found in that conformation. So this is how the reaction proceeds. it took this alkene. Do you know what? While we're doing a Newman projection, let's do a Newman projection of an alkene. This is actually something I didn't want you guys to run into trouble with on the exam. I had that bonus question about a conformation. And I was like, if you look down it the wrong way, it's going to be a little strange to look at. Because a Newman projection of an alkene has something off of the front carbon and the back carbon, but an alkene is planar. So if I look down this, the front carbon has a CH3, and the back carbon has a CH3. Front carbon has an H, and the back carbon has an H. Is it a weird Newman projection? No. A Newman projection is when you sight down the carbon-carbon bond. It's a normal Newman projection. Is it different? Yes. Because instead of having 3 groups off of both carbons, there's only 2 groups off of both carbons. And what you can see is the syn addition. The OHs could have added here, or the OHs could have added here, and we see that the OHs added on the right-hand face. You okay with that? They added syn to each other. They both added on the right hand of this alkene. That would have been anti-addition.
Okay.
Yep. If they had formed by anti-addition, I would have seen one go to the right, one go to the left. But because I see they both added to the right, syn addition.
So it doesn't matter which side.
Correct. It doesn't. And sometimes you actually make enantiomers that way.
Yeah.
Although meso compounds have no enantiomer. All right, well, that means that this is not what the structure would ever look like. So we'd probably draw the structure like this. Because when I go from zig-zig to zigzag, one of those carbons has to rotate. And when it rotates, what's coming forward seems to move backwards. What's backwards seems to move forward. So that wedged OH now looks like a dashed OH because it's rotated. Does it look like the reaction was a syn addition?
No.
From the structure on the right, it doesn't make you think that it was syn addition because the groups are not cis. Well, they don't appear cis. That's the thing. Syn addition doesn't tell you what the structure will look like most of the time. Syn addition tells you how the reaction proceeds. It tells you that the 2 groups added on the right-hand side. When we draw the Newman projection for this structure, we see that the front carbon hasn't changed, but that the back carbon has gone through a rotation. The OHs appear anti to each other. They're directly across, but that does not mean that it was an anti-addition. That's not how they added. They added syn, and then the molecule just rotated. That's fair, right? You guys are okay with this? Let's look at the other example, but let's take it down a similar route. When we look at an anti-addition on this same alkene, it does look like they are trans to each other. But we know that it can rotate. And if it rotates, it looks like they are cis to each other. But again, we can't use cis and trans on linear alkanes for this exact reason. The fact that they can rotate around and switch between cis and trans means that's not a useful descriptor. The structure on the right looks like syn addition, But that's not how the reaction proceeded. The structure on the right formed after a conformational rotation of the product. It's the structure on the left that resembles how the structure was formed. And why would it rotate? To get rid of strain, because in this zig-zig conformation, it's always eclipsed. And when it's zigzag, it's always staggered, and staggered is always lower, despite the fact that it might make it look like it's cis to each other. So when you look at the Newman projection for our first conformation, the conformation that proves the reaction was anti-addition, you can see that one bromine is on the front right, one bromine is on the back left. They've added anti to each other, one right, one left. Once again, that Newman projection of the alkene, this is showing us that one bromine added on the right-hand face and one bromine added on the left-hand face. They added anti to each other. Syn addition and anti-addition will not always help you predict the stereochemistry of the product in its lowest energy conformation. Syn and anti-addition will always help you predict the stereochemistry of the product in the conformation that it forms in the conformation from the reaction. Okay, we'll keep this in mind as we go through the semester because it plays a very important role in predicting our products. Lastly, anti-periplanar. I'm not sure, to be honest, what periplanar actually means. And I'm realizing I actually drew this backwards. I should have had the stereochemistry on the reactant side and then the alkene on the product side. So if you wanted to, you could actually just draw this arrow backwards. Regardless, the periplanar, the anti-periplanar descriptor actually looks at two carbons adjacent to each other to see whether two groups are in the same plane and anti or not. When we take a Newman projection of a chair, I want you guys to remember that sighting down one of the bonds means sighting down the sighting down the parallel bond opposite of it on the other side of the ring, which gives us a double Newman projection. Now, I've given you a filled-in Newman projection already, which shows the carbon with the bromine as what type of carbon? Also, I didn't fill in all of the remaining hydrogens because it can get quite cluttered. But if I leave them blank, like I did here, what do we have to assume they are? They're all methyls, which is not great. So I wanted to fill in all of those lines as hydrogens, but I didn't want it to get too cluttered to look at. So maybe you add in those hydrogens, or just remember they're not methyls. The bromine here is anti and in the same plane as the hydrogen on the adjacent carbon. Without that peri descriptor, anti-planar, I feel like that covers everything you need to know. It's when two groups are anti to each other. And this is most relevant in elimination reactions, which is why the arrow was supposed to go to the alkene, not from the alkene. All right, I kind of jumped over it. The bromine is on what type of carbon at the moment? Remember, in chair conformations, we have two types of carbons, up carbons and down carbons. And the bromine is on which type? How do you know? It's facing up. Well, not just up a little bit either, up axial. And only up carbons have up axial positions because down carbons have down axial positions. So the question is, would this bromine and this hydrogen be antiplanar in the other Newman projection? So in the other chair conformation. So I'm going to draw the other chair conformation, or rather the Newman projection of the other chair conformation, which means we're going to have to do some rotating of our groups. Here's the easiest way in my mind to rotate it. Let's take this down carbon that was connecting both of my front Newman projections, and let's make that an up carbon. Because just by making that one change, my front carbons have both swapped from up carbons to down carbons. So front carbons are not connected by a down carbon anymore. Front carbons are connected by an up carbon. Back carbons are now connected by a down carbon. And let's say we want to keep a very similar perspective. I want to look at the bromine on the front carbon. I want to look at the hydrogen on the back carbon. Where is the bromine if I want to keep the bromine on the same carbon? Keep in mind, I'm doing a chair flip, and my up carbon has become a down carbon. But my up group stays up. Where's the up position on this new down carbon? Up equatorial. So here's the bromine, up equatorial. These are all hydrogens over on the left. Well, that means that everything else here is also a hydrogen. Where is that same hydrogen that I circled before in green? It has to be on the back carbon. So the question is it down to the right on the back carbon, or is it straight up on the back carbon? Chloe? The one to the right here? Because it was down before, down axial. It has to be down again, but now down equatorial. And that is down equatorial. So here are those same two groups that I had before. But now are they anti to each other? Are they directly across from one another? They're not. Are they in the same plane? Are they at least planar? Do you know it really depends on how you define a plane? You need 3 points to define a plane. 2 points is just a line, and a line can exist on a plane, of course, but 2 points is just a line. So if I'm saying bromine and hydrogen create a plane, that can be true, but there are many planes that hold bromine and hydrogen. If I want to figure out if they're planar, if they exist in the same plane as each other, I need a third point. And last time, that third point was the carbon-carbon bond. Looking down the Newman projection of the carbon-carbon bond. Bromine, Newman projection, hydrogen, planar. So if I keep that third point, bromine, Newman projection, hydrogen, is that planar? No, that is angular. It does not define a plane because one bromine is in the front and then the other hydrogen is in the back. So they make a shape like this. They do not make a flat plane. Periplanar positioning of bromine and hydrogen. Sorry, anti-periplanar positioning of bromine and hydrogen, not antiplanar positioning. Later in the semester, we're going to look at elimination reactions, and we will have to be able to identify, are they anti or are they not? Okay, one last thing on this. How often is this hydrogen in red anti-periplanar to the bromine? I'm gonna clarify this. The dashed green hydrogen was anti-periplanar in one of two chair conformations. Or is, doesn't need to be past tense. No. Let me phrase this better. The wedged bromine and the dashed hydrogen. Deal? The wedged bromine and the dashed hydrogen, we're being specific here, are anti-periplanar in one of the two conformations. Now, the wedged bromine and the wedged red hydrogen. Can you discuss amongst yourselves for 2 minutes and predict how many chair conformations these two will be anti-periplanar to each other in?
Well, I guess it depends. Well, you would be looking down a different carbon, so then the projection would be different.
Okay, let me give you a hint with that one. It is true that this hydrogen shows up in this weird spot of the Newman projection that we're using. But can you tell me what is the difference between saying the wedged hydrogen to the left versus the wedged hydrogen to the right? There's not really any difference other than chirality. But the wedged hydrogen at this position would serve essentially the same function here. In fact, I could make that change if you guys want to. Let's just look at, assuming the red hydrogen is the one on the right. I think that will give you a leg up on this analysis. Because now you can reuse the same Newman projections.
In that case, that hydrogen
What is opposite of wedged? Dashed. So can two wedged groups ever be opposite of each other? Weren't these two wedged groups opposite here?
Yes, but they'll be strained.
Here?
Oh, not there.
Yeah, but that's the zigzag.
Ooh. So it depends. Are we talking about rings or are we talking about linear chains? Because if it's a linear chain, freedom of rotation means you can always go from two wedged to being one wedged, one dashed. But when you're locked in a chair conformation, you don't have freedom of rotation all the way around. That means that if you're both wedged, then you're always cis. So we said this, we turned this hydrogen into the red hydrogen, which would be this guy back here. Is the bromine and the red hydrogen anti-periplanar? Are the. Whatever verbiage I need. They're not anti-periplanar, obviously, because I've already designated the anti-periplanar bromine and hydrogen. They're not even anti. They're syn to each other. This wedged bromine and this wedged hydrogen. What about in the back, or sorry, after the chair flip? Now that red hydrogen is up axial instead of up equatorial. Is it now antiplanar? No. So in rings, and this is where it matters the most, in rings, two wedged groups will never be anti-periplanar to each other because they'll never be anti. They'll always be on the same side of the ring. They'll always be cis to each other. But in a linear conformation, any two groups can become anti to each other. You just need to rotate into the right conformation. The wedged bromine and the wedged hydrogen are never anti-periplanar to each other. No, maybe it would be better just to keep it with the same language and say are anti-periplanar in 0 of 2 conformation, 2 chairs. Because again, all of this applies to chairs. When we talk about linear chains, freedom of rotation lets you have groups sometimes antiplanar and sometimes not. Gavin.
How did we know that the wedged hydrogen was coming off to the right and not the left?
There's no space to put a hydrogen there. That's a CH2. Yeah. Here's that back carbon is right here, and to its left is a CH2 before it connects to the back carbon of the other side of our Newman projection. The other reason we knew this is because of chirality, essentially. If I really am to put my perspective down to look at that carbon-carbon bond, the carbon group is literally going to the left, not the hydrogen. And the hydrogen is literally going to the right. So on the Newman projection, it should reflect that literal perspective. Good question. Did that answer it? Okay. All right, questions about regiochemistry and stereochemistry terms that we'll be using in our reactions? Great. We're going to talk about solvents briefly. 3 major types of solvents. Nonpolar solvents like hexane and Legroin, also referred to as petroleum ether, which is kind of an interesting name. You guys notice what functional group is not in petroleum ether? There's no ether. And that's because the ether they're talking about is like the essence. You guys watch Marvel? And there's the ether Infinity Stone. It's not called that. The reality Infinity Stone was an ether before they captured it. And it was just this essence. This is the gas phase that sits above crude oil. It's the very lightweight, low intermolecular force compounds that sit over larger carbon chains that are isolated with crude oil. So when you take crude oil, petroleum, and you just harvest the gas that's sitting on top, you're harvesting its ether, its essence, and you get petroleum ether. Love it. We don't use these all the time in organic chemistry. Typically, we use it if we need two different phases, a highly nonpolar phase and then a more polar phase, so we can separate out things. Then we have two types of polar phases. Polar aprotic. Aprotic there is telling us what? Lacking protons. Yes. Non-acidic. Because remember, a proton is just H+. So if we're saying it's aprotic, we're saying it does not deliver H+. It is not acidic. Does that mean that these will have no hydrogens? Correct. It just means the hydrogens present won't be a part of acidic groups. So you'll notice all of the hydrogens here are CH groups. Very much not acidic. Acetone is our first compound. You know acetone as nail polish remover. An IUPAC name for acetone is actually 2-propanone. It's a 3-carbon chain with a ketone at the second position, 2-propanone. Acet, this ACET prefix, actually means 2-carbon carbonyl. Acetic acid is 2 carbons carboxylic acid. Acetaldehyde, 2 carbons aldehyde. Acetone is famously not 2 carbons, it's 3. But whichever direction you approach the carbonyl from is a 2-carbon carbonyl. So it's the ketone of 2-carbon carbonyls. I hate it here. I didn't come up with any of these names, and I wouldn't have named it that if I could have stopped it. This is dimethyl sulfoxide, but it is better known as DMSO. DMSO will be one of the byproducts from a reaction we do later from DMS, dimethyl sulfide. The next one is DMF, which stands for dimethyl formamide. Now hopefully you can see the amide group. That's the nitrogen bonded to the carbonyl. Form actually tells you a 1-carbon carbonyl. So the same way acet tells you 2-carbon carbonyl, form tells you 1-carbon carbonyl. So usually formamide is an aldehyde with some other functionality. Form aldehyde, aldehyde on one side, aldehyde on the other. Formic acid, aldehyde on one side, carboxylic acid on the other. Formamide, aldehyde on one side, carboxylic acid on the other. The next structure we have is ethyl acetate. And next to it is diethyl ether. Sometimes written as Et2O because it's 2 ethyl groups connected by an oxygen. We use a lot of diethyl ether in lab, and that's because it's relatively inexpensive, fairly good at separating from water and nonpolar solvents. The problem with ethers is that they form peroxides over time. Peroxides are O-O single bonds. So this reacts with oxygen in the air, and it adds an extra oxygen in there. Peroxides are shock sensitive, so if you drop it after it's formed a lot of peroxides, or even if you twist it while you're opening, you can actually detonate the peroxide. Quite dangerous. So we use we use ethers only because we use them enough that we run out of them before they expire. But if we were ever to cut back on how much ether we use, we would need to be more cautious about throwing it out after it expires.
What does that detonation look like? Is it like combustion, or is it just like a pop, or like?
If it's a small amount of peroxide, it might be a pop. But if it's a lot of combustion, or if it's a lot of peroxide present, just think of a bomb. It would be a bomb. Mm-hmm. Which I guess it would be a type of combustion. Yeah. The next structure is also an ether. This one is called THF, which stands for tetrahydrofurane. Furane is an organic compound that we talk about in OChem 2 a lot more. It's an aromatic compound. And furane itself is not that great of a solvent, but add 4 hydrogens across it, and you get THF. You'll see THF in a number of your problems on active. Where we use diethyl ether a lot in lab, other people use tetrahydrofurane a lot in lab. Okay, and the last one is CH2Cl2, often referred to as DCM. Its full name is dichloromethane, although another common name for it is methylene chloride. This would be a stretch, but do you guys remember what methylene means? I do believe I gave this to you. Yeah, how can you have a carbon-carbon double bond with just one carbon, though? No. Good question, though. If you do the degrees of unsaturation, the 2 chicken rule on this, 0 degrees of unsaturation. Methylene means CH2 in any context. If you have a CH2 group, you can refer to it as a methylene. In the same way that a CH3 group is called a methyl, CH2 is methylene, and CH is methine.
So does ene just mean 2 bonds because it's carbon to 2 hydrogens?
I wish it did. I wish ene just meant 2 bonds. Look, again, I wasn't in the room when they decided on all of this. All right, polar protic solvents, meaning these solvents can act as acids. Doesn't mean that they have to be strong acids. It doesn't mean that they have to give up their proton willingly or quickly. It just means that they can be acidic. So of course we see things like dihydrogen monoxide. Or DHM. You guys ever called it that? No, I'm just kidding. We don't call it that. Methanol. Sometimes written out as MEOH because we can abbreviate CH3 with ME. And did you know that you can write these chemicals forward and backwards? So methanol can be written as CH3OH. Methanol can be written as HOCH3, which means abbreviating methanol with ME and then spelling it backwards. Home. Don't drink methanol, by the way. Did I tell you guys that story yet? You can go blind if you have a small amount. You have a normal amount of grain alcohol or ethyl alcohol in equivalents of methanol, and you'll die. There was an underage party down in Arizona a number of years ago. A student, maybe that was working in a chemistry lab and had access to chemicals, was like, I'll bring the alcohol for the party. Spiked the punch at this underage party with methyl alcohol and killed dozens of college students. They all died. When methanol gets oxidized in your body, ethanol gets oxidized into acetic acid, or acetaldehyde. But methanol gets oxidized into formaldehyde and formic acid. So it's a lot worse for you. There was an episode of House that actually introduced a character with methanol poisoning. And legitimately, the way that they handled it in House and in real hospitals is that you outcompete the metabolic pathways of metabolizing methanol with alcohol. So they, in this episode of House was just doing tequila shots with this guy, because the more ethanol in his body, the less methanol would be metabolized. So the methanol could get excreted while his body was working to metabolize ethanol. But it was literally just a statistical thing. If you're going to metabolize both, then try to have more ethanol so it only metabolizes that and doesn't kill you. Gavin?
Random tidbit. I heard in Southeast Asian countries, sometimes you have to worry about cheap alcohol and methanol poisoning.
I believe it.
They do a lot of home brew stuff.
That's a good point. If you don't purify it well and you end up with too much methanol, you would probably go blind first, which is just go blind, right?
This is unrelated. I was just gonna ask you what you know about the chemistry behind the use of methylene blue as a solution for lidocaine.
I don't know anything about methylene blue.
All of it.
Sorry. But yeah, come back and share it with us. Okay, here's ethanol. And the next one is isopropyl alcohol, which you all know better as rubbing alcohol. Isopropyl alcohol or isopropanol. And if we wanted to abbreviate this like we did methanol and ethanol, ethanol was abbreviated ET for ethyl. If we wanted to abbreviate isopropyl, we could use PR, but that would be confused with propyl. So we use a lowercase I and then PR to give us isopropyl alcohol. That last structure on the right is acetic acid. And the way that we often abbreviate acetic acid is ACOH. So we are assuming that AC means a CH3 bonded to a carbonyl, which, if you remember, that's what the acid part meant, a 2-carbon carbonyl. CH3 carbonyl, CH3 carbonyl, acetone. CH3 carbonyl, acetate. CH3 carbonyl, acetic acid. So AC is representing our acid group. In terms of solvent, nonpolar and polar aprotic solvents are generally inert. They don't react inside a reaction at all. Polar protic solvents can be inert, meaning they don't react in the reaction. But most of the time in our class, polar protic solvents engage in the reaction, which make them reagents as much as they are solvents. So let me ask you this. What is the role of a solvent if it's not a reagent? Why even use an extra chemical that doesn't play a role in the chemical changes? Catalyst? To dissolve things. So catalysts engage in the mechanism. but then are not consumed in the mechanism. Catalysts change the way a reaction proceeds, but they're neither produced nor consumed. Solvents can be catalysts. Generally, they're not. Solvents dissolve things. They act as a medium, a place for things to happen. Solvation is a process by which solvent molecules hold on to a solute molecule. So if this is my solute, and perhaps my solute has the ability to do dipole-dipole interactions, so it's got partial charges, then my solvent can actually align itself so that it has positive or attractive interactions between the solute. And that is solvation. There's another process called solvolysis, and solvolysis is, I just got to make sure I can spell it right, a reaction with the solvent. If the solvent is a reagent, then the reaction is a solvolysis reaction. Kind of like sometimes we just swim in the pool and we don't drink the water, but we also drink water, not in a pool. Sometimes you can drink water while you're in a pool. Different roles of water, different ways that they can come in. When we run a reaction, we need molecules to run into each other. We need them to run into each other with enough energy to make and break the bonds needed. We need them to run into each other with the right orientation for the bonds to break and be made. And the best way to get molecules to run into each other with enough energy and with the right orientation is to surround them by other molecules that you can heat up so that you can get them moving around. So solvents typically serve as just a medium, a place for a reaction to occur. Sometimes they do act in the reaction as well. Solvolysis. Questions about solvents? On active, you will see some solvents written that are inert. They're just there to mediate the reaction. But on materials that I give you, when you're studying for the exams, the only time I introduce solvents is if they play a role in the reaction. So these solvents, I would just get familiar with them as inert pieces of information in the reaction. These serve no role. They'll be involved in nothing in the reaction. Polar protic solvents, when they're written out, they serve a role. They're doing something. All right. Well, the last thing that we have to talk about is how a reaction proceeds. First, let's introduce the reaction coordinate diagram. We show energy on the y-axis sometimes. Sometimes we show delta G. Sometimes we show delta E. Sometimes we show delta H. And on the x-axis, we put the reaction coordinate. Can you guys describe what a reaction coordinate means?
Place where the reaction occurs based on the axis.
A place where the reaction occurs, meaning
Based on,
whether it happens in West Valley versus happening in Taylorsville?
based on our x and y axis, whatever those variables are, causing a reaction to occur at that point.
What's causing it to occur?
How much energy is needed for the reaction to occur.
That's what the reaction coordinate means, or that's what the y-axis means?
I mean, that's basically what the y-axis means.
So what about the x-axis? Why are we calling it reaction coordinate? The what? Like first order, second order, third order?
No, like the order in which, like the different steps.
The steps of a reaction, yeah, the sequence in which things happen. So it's not a physical place in space. Instead, it's a description of how changes occur and the energy associated with them. The reaction coordinate, some reaction coordinates are bidirectional. We can show a starting material that can either form one product or another, and we can actually show two directions of a reaction coordinate, two different reactions from the same starting material. There's several components of the reaction coordinate. First, the reagents or the starting material. You guys okay if I abbreviate it SM for starting material? The starting materials go through some change. And we're going to talk about in which reactions, what changes should we predict. But when they go through that change, that will take energy to break bonds and sometimes make bonds. At the pinnacle of this energy is a transition state. And a transition state is a theoretical structure. No transition state has ever been isolated, characterized, and proven. It's all theoretical, but it's based in good evidence. A transition state is where bonds are not formed or broken. Or the way that I say it is bonds are actively forming or breaking. A transition state could have more than 5 bonds to carbon. But that's because it doesn't really have 5 bonds. There are bonds forming and breaking, so there's really just 5 things around the carbon. And it's very high energy. So much like those conformations we were talking about, the highest energy conformations, you'll never isolate it because a very small sample actually has it. You can't isolate the transition state because as soon as it gets to that energy, it's going to roll one way or the other. And the question of when a structure is in that transition state, is it going forward in the reaction coordinate or is it going backwards? The answer to that question is it's not going forward or backwards. It's just at the pinnacle, and it could go either way. A transition state is not inherently moving forward or backwards in a reaction. After a transition state, after some change is made, then we get to our reactive intermediates. I'm going to say sometimes, because not all reactions have intermediates. In some reactions, it's just one step. Starting material becomes products. But many reactions have these intermediates that are at higher energies than the starting materials or products. So they're likely to continue reacting, reactive intermediates, as opposed to stable intermediates or non-reactive intermediates. Reactive intermediates, of course, can't be the product. So after reactive intermediates is another transition state before we get to our products. Now, I know that the diagram I have for you guys has an additional transition state and product. This is just generically the components of our reaction diagram. So what I would like you guys to do, I'd like you to figure out where these components of a chemical reaction belong. Notice that you're given water and tert-butyl chloride as your starting materials. Then you're given tert-butyl alcohol and hydrochloric acid as your products. I want you guys to work together and decide which changes make sense to happen first. Which reactive intermediates form at which stage, and what transition states relate starting material to intermediate.
Is 4 a second reaction intermediate?
It is, yep. So this is just a generic template. I want you guys to fill this in. By the way, I'm not making you guess between reactive intermediates on the bottom and transition states on the bottom. Is it easy enough to tell what's a transition state option? Because it has what? Brackets. And this little thing is called a double dagger. So when you see that double dagger, you know you're talking about a transition state. All right, let's take 5 minutes, work together, and fill them in based on what changes seem plausible.
This is right.
Mm-mm.
What's wrong?
2 and 4.
Oh, this one comes before that. This should be 4.
Yep.
That makes sense. 3.
What are you thinking, Andrew?
I was thinking 1, 2, 3, 4, 5.
Close. But these two wouldn't quite make sense in the places you put them, because this one is making and breaking a bond between C and O. But this one already has it. And you were saying to go from this to this, right? Starting material to this,
Yeah.
this intermediate to this intermediate. What's the change that happens here?
Okay.
The CO bond forms.
So, I guess in this transition, the chlorine attaches to the hydrogen, but then it ends up separate anyway. Here.
Well, if this is the last step, that's how we get rid of that
Oh.
second H.
So it breaks there.
Good.
Okay.
Now that you've thought about it for a while, let me add something. On the one that you're looking at, what are the total things changing? What bonds form? What bonds break? And then think about which steps allow you to do those in a process that makes sense. Think about what forms, what breaks. Feel good?
Well, I never feel all like, but I feel okay.
There's 2 transition states I'd switch. 2 of your transition states need to switch out. Got it.
Got it? Okay, cool.
Oh, I didn't look at yours. Sorry.
Almost had you there.
All of your transition states need to change.
So close.
This is really bad.
Did I get it right?
No, 2 of your transition states need to change. Yep. Got it. 8, 6, 7, 5, 3. How's that song go?
8, 6, 7, 5, 0, 9.
There you go. That's it.
I think I'm too young for this.
My mom's 60.
2 of your transition states need to switch. Not you. Sorry, I was talking to him.
We have the same thing.
Yours are good. Well, you couldn't.
We have the same. Scared to write in pen.
I didn't fix mine, I just erased it.
I tried
Isn't it an erasable pen?
No, that's just the top of it.
Oh, it really looked like an eraser
I
in there.
know.
Erasable pens are the way.
It doesn't feel like a real pen though. 'Cause
Yeah,
half
it
the
does.
time
Oh,
the
wait, now
pen
you have
is
what
the
I have.
permanence of what you were making.
What bonds do you see breaking over the course of this chemical reaction? Starting material to products. What bonds need to break? H2O is not a bond, unfortunately. An OH bond breaks. A carbon-chlorine bond breaks. Anything else? I agree. What bonds form?
Hydrogen, Cl.
Good. H to Cl bond forms.
Oxygen to carbon.
Carbon to oxygen bond forms. So we could imagine a world where this takes 4 steps. In each step, 1 bond breaks or 1 bond forms. But this did not take 4 steps. We can actually count the steps in a reaction by counting the transition states. We call these elementary steps, the smallest change during a chemical reaction. Individual changes in a reaction. Some reactions only have 1 elementary step. Other reactions have many elementary steps. This reaction has how many? 3 elementary steps. What that means is there must be a step where 2 of these changes are happening at once. There must be a step where a bond forms and a bond breaks, or 2 bonds form or 2 bonds break. Because if it were each change happening in its own step, there'd be 4 individual steps. The options that were given to us in the transition states. One option is that the carbon-chlorine bond breaks. Another option is that the carbon-oxygen bond forms. And the last option is where an OH bond breaks while an HCl bond forms. So we have to try and rationalize what is feasible here. Could I form the CO bond before I break the CCl bond? If I form the CO bond, that would mean, without breaking the CCl bond, that would mean my carbon would go to 5 bonds. That doesn't make sense. Could I form the CO bond while I break the CCl bond? Yeah. But that's not one of the options given to us. So the first thing I have to do before I can form the CO bond, I have to break the CCl bond. So that bond is shown as a dotted line, which means it's not formed, but it's not broken. It's stretched. And after it stretches, the carbon takes on a positive charge, the chlorine takes on a negative charge because electrons go to the more electronegative atom. Then I can form the CO bond. And again, in this transition state, it's a long dotted line because it's not a bond formed, but it's not a bond broken. It's actively in that stage of forming or breaking. Remember, at this structure, it could fall backwards to the carbon with the positive charge, or it could fall forward to the next intermediate. And these are transition states, so oftentimes we draw them in their brackets with this double dagger. The next intermediate that we find is this protonated oxygen, this protonated alcohol, plus chloride. And our last transition state would be to predict that the OH bond breaks because the CLH bond is forming. Process of, well, this one gave you a lot of clues. We knew what the possible structures were, and then it was just a process of determining what is feasible first. I can't make the CO bond until after the CCl bond is broken. So I broke that bond first. Then I could form the CO bond, which I needed before I could have a structure that broke OH and formed HCl, but had a permanent CO bond. You guys agree that this CO bond is not breaking or forming? I did draw something weird though, didn't I? I forgot my other hydrogen. This CO bond is not forming or breaking. So by this point in the mechanism, that CO bond had to have already formed. And for that CO bond to have already formed, the CCl bond must have already broken. In general chemistry, we talk to you about state functions. We say that the change from starting material to product is an absolute change. It doesn't matter how you get there. Another way I could have run this reaction is to break literally every single bond. Break every CH, every CC, the CL, the OHs. Break all of them apart, which takes a ton of energy. I can't draw it anymore because I ran out of board space. And then I could recombine all of the bonds in the ways that I need. Recombine all the CHs, all the CCs, recombine the CO, combine the H and Cl, and I could come back to exactly that same product energy point. It's a state function. It doesn't matter how you get there, it just matters what change you got. No more. That's general chemistry. In organic chemistry, one of our roles is to provide an explanation of what bonds formed, what bonds broke, how the electrons were moved during that process. So on the last page of our worksheet, we have reaction mechanisms. How did the reaction proceed? I want you to think of the reaction coordinate as something that can be compressed linearly into a mechanism. Rather than looking at what energy they're at, what's the highest energy, what's the lowest energy, we're just going to look at the nature of the structure, and we'll use electron arrows to say when this bond breaks, the electrons are taken to the more electronegative atom. This bond forms because lone pairs were donated to form a bond. So, first, a one-step mechanism. I am sorry, we're not going to go over this one, but we can always come back to it if you guys want more practice. A one-step mechanism is very simple. It means that the reaction coordinate diagram looks like this. Starting materials to products. And we can still use this idea of spotting the difference. What bonds form, what bonds break. We can see that a CO bond forms and a CCl bond breaks. Well, you can't see it because I didn't draw it up here. So now how do those bonds form? How do those bonds break? So I think I've given you this tip before. I'm going to give it again. Bonds break to the more electronegative atom. Bonds form from the more electronegative atom. Carbon-chlorine bond breaks. How many electrons in the bond between carbon and chlorine? 2 electrons. Because that's what we've agreed a line means. A line means 2 electrons. So here are the electrons. That's the start of my arrow, because those electrons are no longer going to be bonding electrons. The question is, where do those electrons go? They can only go to chlorine or carbon. These electrons will never be lobbed into space towards some other atom. These electrons can be taken by one atom or the other, and we said that bonds break to the more electronegative atom. So we say the bonding electrons are now taken by the chlorine alone. Are there any more bonding electrons between carbon and chlorine now? Correct. There are no more bonding electrons, which means the bond is broken. And chlorine took them, which means I now have a chloride ion. And I need to form a bond between C and O. Where will those electrons come from? They have to come from O because bonds form from the more electronegative atom. It's the electron-wealthy atom. It can decide to share electrons. Now we know that OH minus is actually 3 lone pairs on hydroxide. So we should show the reaction, we should show the arrow coming from one of the lone pairs because those are the electrons. I will say 90% of the time you could draw this from the negative charge because the negative charge implies a lone pair. On hydroxide, the negative charge means an extra lone pair. But it never hurts to just draw it from the lone pair. Oxygen is not losing those electrons. It's sharing them. Why would oxygen lose electrons? It's not good at losing electrons. It's very electronegative. But it sure can share electrons. We know that oxygen shares electrons. It likes to have 2 bonds. When it shares one of its lone pairs, it only has 2 left, and it's a neutral 2-bonded oxygen. That's the mechanism. That's how the electrons change in order to form the products.
So when the oxygen is sharing electrons with the carbon and creating that bond, that's why it's fine to draw our arrow so big, because you can't draw it at cross with the chlorine because it's not sharing, it's giving.
So your question is about how do we draw the electron arrow?
No, well, my question was just said, like you said, the
You can do whatever you want as long as they start and end at the right spot.
well, you said like with the chlorine breaking, our sigma, our electrons on our sigma have to go to the chlorine or the carbon. They can't just go out into space. And that's not what's happening with the oxygen, right? It's not lobbing its electrons at the carbon. That wouldn't be allowed.
Correct.
It's going over the joint.
Yes.
Okay.
Can you guys finish this sentence? I've said this a lot this semester. I think you should be able to finish it. I was thinking about this last night as I was planning for this lecture, not sleeping. Everything is just
Terrible.
Is that something I've said a lot this semester? Everything is just terrible. Everything is just relative. I don't think I've said either of those. Everything is just magnets.
Right, you have said that.
Everything is just magnets. So what type of magnet is hydroxide? A negative one, but do magnets really have negative or positive? Magnets have north and south, which is the analogy to electric charge, positive and negative. So when I say it's a negative magnet, there is no such thing, but it's the negative equivalence of a magnet, yeah? So hydroxide is a negative magnet. What's it going to be pulled towards? Something positive. Where's the positive? On the carbon, because chlorine is pulling electrons away from carbon. So why is the bond forming from hydroxide? Why is the bond forming from oxygen? Because oxygen is getting pulled in like a magnet. It's got this negative charge that is attracted to the partial positive of the carbon. Okay, that's a one-step mechanism. Two changes, both changes happen at the same step. In the reaction coordinate, we're not saying a physical change in space. We're just saying the energy that happens as they move through space. The mechanism is trying a little bit harder to show the physical movement through space, having those magnets find each other to make the change. But it's really hard to show a three-dimensional reaction mediated by a solvent on a two-dimensional stagnant board or piece of paper. So we use arrows to show where the electrons come from and where they need to go, which can help you visualize how do these molecules need to interact in space in order for the reaction to occur. But we won't actually be showing how the reactions happen in space. Imagine, if you will, that I show you a parking lot and a car, and in one image, I show you that the car is not parked. And then I show you another instance, and you see that the car is now parked. How would you add arrows to one side to show how the second side formed? You'd say this car moved into this empty spot. Am I doing a good job showing the car animated, moving into the spot? Kind of. I'm doing the best I can with that arrow. Do you know what a lot of people accidentally do with their electron arrows? They draw their arrows backwards, as if to say, the spot came to the car. What? A lack of car moved to the presence of car, or the presence of car moved into the lack of car? Which is, again, in this analogy, would be like saying, having an electron arrow that looks like this. The nucleus moved to the electrons, but these are not nucleus arrows. They are electron arrows. So I should always see my arrow start from my electron source and point somewhere else. Point to a nucleus or point to a bonding area to make more bonds in that area. So we're going to do more with mechanisms throughout the rest of the semester. I have more problems for us on this worksheet to just get introduced with mechanisms. Also tomorrow, we're going to do an activity with predicting mechanisms. And then we're going to get into alkenes. After we broadly go over alkenes as a functional group, we're going to move into alkene addition reactions. We are going to be learning more than 8 alkene addition reactions for this unit. And then the following unit, Unit 5, our last unit, is like mostly reactions. So we'll be going through that at the end of this week and all next week. Okay? See you guys tomorrow. Thank you for your time.